So we're going to continue our lecture on thinking about building neural network architectures and thinking about input-output to functions and thinking about the kind of things we can do, whether it be classification, prediction, or just simply building state estimates of different high-dimensional systems. So this is going to be out of section 6.2 out of this book here, this new book by Bruntman Kutz in Cambridge. If you want to follow along, all the lectures are here, databookuw.com. So go there. All the links to all the lectures and playlists that you need around this are there. So the first lecture basically considered sort of neural network architectures where you have an input layer to an output layer. Now the output layer could do different things. It could do a reconstruction. It could do a classification type task. And part of what we want to look at is what kind of architectures can we play around with here where your input data is mapped to an output layer. And in the middle you have different structures and different nonlinear functions or linear functions. In the first lecture that we did, we talked a lot about the input being, or these layers being, linear maps from an input to an output. But now we're going to make this be allowed to be nonlinear maps from the input to the output. Now this is a generic structure here, and most neural nets generically are going to have nonlinear maps from input to output, and we'll talk about some of those. But I want to come back to this here, is what we did in the first lecture. Remember, was go from input layer to an output layer. And the data we played with was images of dogs and cats. So what we're going to come back to here is look at that same data set and the images of dogs and cats that we did previously. What we did is we basically trained this just to be a linear map. And you saw that was quite effective, actually. This just becomes AX equal to B. But now we're going to let this be some kind of nonlinear function. So now we're going to say this isn't just a matrix A taking me from the input to a label, which is a dog or cat label, but I want this now to allow to have nonlinear interactions or nonlinear weighting functions that take me from my input space to my output space. Okay, so the nonlinear transfer functions, what kind of things can we have? Now what we did previously was just a linear map. I take my f of x and I move it, it's just x. So now you just, whatever that function is, you're going to take that function and carry it over to the output. Okay? But there are a lot of different types of transfer functions that can happen in this, or what are called activation functions in neural network language. So for instance, here is one, a binary step. I'm just going to give you a set of them that are fairly common. The binary step is 0 and then 1. So it's like a Heaviside function, which is what we normally would call it in applied mathematics. So here you go, values of 0 and 1, depending upon the exit values. Here is a logistic soft step, essentially, with the data. And you can see what it does. It sort of has a sigmoidal shape. So you start off here with 1, and then, as x goes to negative infinity, right? So this goes to 0, but then as x gets very large, this goes to 1. So it's from 0, comes up and goes to 1. Okay, so that's typically used in logistic regressions. We also have the tanh function, which is very much like logistic, but now it just has a different functional form, which is a hyperbolic tangent, which goes from -1 up at near 0 to 1 at infinity. And finally, this is one of the most commonly used, is a rectified linear unit, ReLU. So ReLU is a very commonly used form, which is very simple, by the way. It's 0 for x less than 0 and linear above that. So it's a nonlinear function constructed of two linear parts. Now ReLU is very powerful because one thing it doesn't do as x gets big, it doesn't go towards a flat value as you would in tanh or logistic map. Oftentimes it's very hard to compute gradients once you've gotten yourself in a flat position, whereas ReLU allows you to have meaningful values even far away at x is large. The other thing that's nice about ReLU is very easy to piecewise differentiate. So what we're going to see in a lot of activation functions, and in particular in upcoming lectures, we're going to talk about the back propagation algorithm. Backpropagation wants to differentiate these activation functions. And so all of these actually are very simple derivatives to compute, and a rectified linear unit is trivial to compute, but it's done piecewise. So these are the different kind of activation functions you can impose instead of a linear map, which we had done in the previous lecture, which was here. We're going to now generalize it and make something a little bit more interesting happen by allowing for nonlinearity in from the input to the output. Okay, so that's what we're going to try to go after. And what I want to do is now is give you a little MATLAB code. We're going to go back to the dog cat images. And in this MATLAB code, what we're going to do is run through some of this and do a classification task with now using nonlinear functional responses. Okay, so here we go. I'm pulling up my MATLAB. Here it is. So this is the full code, which is going to train a neural network to allow us to do a classification of this dog-cat image data set, but now with a nonlinear transfer function instead of just ax equal to b. Now it's a nonlinear mapping between one and the other. So let's walk through this code a little bit. So I start off with all the standard clear all, close all commands. Let's start here with this set of lines of code. So the first thing I'm going to do here is I'm going to load my data. So I have my cat data and my dog data. Now these are cat and dog images that have been wavelet transformed. And as we've been playing with last lecture is to sort of classify and build a classifier which can identify the difference between dogs and cats. So what I need to do in any neural network architecture is I need to train the network. And so to do that, you need a training data set, but then you also need to withhold some of the data so you can test what you've done with that in building a model out of that neural network. Okay, so this is what I'm going to do next, is I'm going to basically take my data here, and what I've done is I've created a data set X and X2. Now the data set X here is going to be my training data. And what I'm going to do is take the first 40 dog pictures, 40 cat pictures, and put them together. That's my training set. So I'm taking a subset that I'm going to use for training. And in X2, which is here, is I'm going to take now the remaining 40 dogs and cats, and I'm going to withhold them. They're not going to be part of the training process. I'm going to hold them out. And then we're going to build a model using the data X and test it on the data X2. So it never sees X2. So I train it on X, build the model, see how well it works on X2. Now this little toy example is going to highlight a lot of different things, in particular that the neural net is going to do very well in building a model that's going to classify very well in the training data, but not work well on generalizing towards the data that's been withheld, which is the test data. Okay. Typically you would do something a little more sophisticated, and we'll talk about this later, which is in the modeling and model selection and regression chapter, you would do something with cross-validation. Here we're just going to do just a very simple model design, and we will leave cross-validation for later. So what do we do next? I want to provide labels. So I'm going to label both data sets. I'm going to label them, in fact, the way I want to do dogs and cats is going to be in the following way. So let me just show you how I'm going to set this up to label the dog-cat data. And here it is. So if I look here, this is how I'm going to set up the data set. Here's my dog. Here's my cat. So I'm going to try to take the input data and map it to a vector y, which is 1, 0. And that's a dog. And try to map the cat data to the vector 0, 1. This is the cat. So I'm going to take the input space, which is pixel space, train a neural network to take it from the input space, which is pixel space x, down to output space y, which is a classification which should come out 1, 0 or 0, 1. So either a cat or a dog. All right, so that's the objective. That's my target. Those are my targets that I'm going after in the neural net, from the input space to this target space, which is now a classification task. Okay, so back to the code. That's what this set of lines are doing here, the labels. So what I'm going to build for those x and x2 data, for the x data, I have 1s, 0, and then 0, 1s. Okay, so these are the dogs and cats. So I've labeled the first 40 dogs as 1, 0, and the first 40 cats as 0, 1. Of course, really what you'd want to do is just randomly draw from the dogs and cats, and not just take the first 40. But for this simple example, I'm just showing you how this architecture would work. Okay, but those are the labels then associated with the data. And now we can go and train a neural network to do the classification. What we had done previously is we had just simply done AX equal to B on this to find solutions. And we had promoted both sparse solutions to the AX equal to B and also L2 type solutions to AX equal to B. And you saw the difference there. But now we're going to train a neural network. And here is what we're going to do. We have to define the network. So neural networks in MATLAB or Python, scikit-learn, TensorFlow, they're all pretty easy to do. They have very similar structures, which is you impose a network style and architecture. So what we're going to do here is define the net, here's the net, as a pattern identification network. So pattern net is sort of the built-in MATLAB pattern identification network. And we're going to have 10 hidden units in it. And we're going to train this using a stabilized conjugate gradient method. That's the train SCG. You can provide other type of architectures there. If you look at the help pages on MathWorks, it'll tell you all kinds of things that you can put into there, as well as options for the pattern net network that's there. So I can then specify properties of this network. So for instance here, network layers, I want to do one layer. First layer, transfer function is going to be tangent tan sig. So this is the hyperbolic tangent, essentially. So what you're doing is now specifying the activation function you're going to use, in other words, the nonlinear transfer function you're going to apply. You can use tan sig, you can use ReLU. There's all kinds of options here. So you just specify what you want. You can even specify linear, which would get you back exactly to where you were previously, which is the linear model that we built before. So once I've specified the network architecture, then you go to do the training of this network. And it's basically as simple as this. One line. And this is the canonical way you define these in MATLAB or TensorFlow, Keras, PyTorch. The network, train. There's the command. Train, and what you're going to tell it to do is train. What are you going to train? The network you've defined. You're giving it the data x and the labels. There it is. So you're telling, build a map from x to y, which is the labels in this case, and with the network you specified. And what it's going to bring back to you is an object called net. So net is the output of this. So you give it the training data, and you gave it the task of going from the input space to a label space. So cats and dogs going to a plus, a 1, 0, or a 0, 1. That's what it's trying to train to do. And so that's it. So that is going to actually, this is where so specifying the network does not cost you any computational time. When you do the net here and train, we're going to run this in a minute, you'll see that this thing will actually start to run through this and train it using this stabilized conjugate gradient method for doing the optimization itself. What's going to come out of this is a few things. So we're going to see some graphics that come out of this. That's going to give us important information about how this neural network handled things. So first, it's going to ViewNet is going to give us you'll see here, a graphical user interface, which is going to give us the statistics of what happened during the training process. So as this thing was doing its optimization and reaching a certain threshold of error, what it's going to show you is diagnostic features that you can use to understand how well it did in learning a model that maps the cat-dog pictures to a label of 1, 0, or 0, 1. Okay, so I'm going to also do the following then. So I train this. I'm going to say, I'm going to take the data now, and these are 2 lines of code here that are going to tell us how we did. So first, I can take this trained network, net, and throw x into it. X, remember, was the pixel space of the dogs and cats. And the output is y. That's the target. So for all the data I put in there, give me the label y. Now, x and y were the training data. So when I do this first line of commands, y equals net x, what it's doing is telling me how well I did on my training data. Okay? So in other words, I'm going to build a model on the training data, and the question is, how well does the model fit the training data? Now the problem with that is typically you can overfit this data. So what you really need to do is look, how well does the model do if I actually look at the test set that I withheld? So that's what y2 net x2 does. Remember, x2 and y2 are the labels and the pictures of the dogs and cats that were withheld. So they never were part of the training process. So y2 net x2 is going to give me, take all the dogs and cats I hadn't seen, run it through the network, provide me a label, the label being 1, 0 or 0, 1, and then I can ask, how well did I do? How well did this network train itself so that I can actually evaluate the quality of the network? Okay, a couple performance metrics we can look at before we run it. So I can look at the performance of this here with the perform command. So what you do is you take the perform command network, you put your labels in, and put your y in. So labels were what the truth was, y was what the code gave you. Okay? And really what you'd want to do is put in the labels for the second set against y2. But this will give you essentially the percentage that you got correct, and so it'll tell you some metric about or what your error rate is. Okay? We can also look at this from the what's called classes. So you can take the outputs, which is y and y2. Remember, these are going to try to give you either a vector of 1, 0, 0, 1, and you can take these vectors to essentially what this is going to be, take the vector to an identifier, which is the identifier, which is a label which is either a 1 or a 2. So did you get the label is a 1 or a 2 in this vector in command. Okay? So it's going to give you a class. If you have 2 classes, the first class is called 1, second one's called 2, the third one's called 3, and so vector_int is just going to give you the label 1, 2, or 1, 2. So classes 2 and 3, classes 2 is actually giving you how well it got correctly the first training data. Class 3 is telling you how it did on the withhold data set. So let's run this, look at the diagnostics, and also then look at the performance. So I'm going to run this here. And when you run this, what's going to pop up here, this is the training window. So a couple important graphics come up here, and let's walk through them. And I will actually put these in larger screen size so we can look at them. So let's first start here. So what you typically pop up in MATLAB is a little icon or graphical user interface like this. And what it tells you is the structure of the network. Here you go. So what you're going for is your input level. And it's telling you that your input has 1024 dimensions. So that's the pixel space you're working in. The vector x coming in is 1024. And the output space over here is 2. And what you said is that you want something here that actually has size 10. So let me just go back and remind you that that size 10 was specified right here in pattern net. So when you do the pattern net, you can specify how big you want that middle to be before it drops down to the 2 output switches, or 1, 0, or 0, 1. Okay, so that is what this thing will do. Okay, it gives you some performance metrics. You can look at any of these hit any of these buttons here, and it will produce plots. So for instance, here is how it did during the training. So it's going to give you different metrics here about the error, the cross-validated error. And by the way, notice here that this drops down, and the red is very important because what it does internally is it actually does a cross-validation by itself. So it builds a model, but it realizes that whatever our model will do, I'll overfit. So what I'll do is I'll take random draws, build a model, cross-validate, and you can see that it actually has a fold point here before the error starts going back up. And we'll see that in a moment when we look at how well this model does on the withhold data set that we took out. Okay, so that is, for instance, in the performance chart. Here's the error histogram. You can look at various features of this. The error histogram is interesting because it actually tells you it did very well, actually. So you can start looking at this, how many did it classify correctly? And in fact, if I show you this, maybe this is a better place to show it to you. And there's also, by the way, a confusion matrix. Let me just finish showing you this. This is the confusion matrix that it gives you for this two-way classifier, dogs and cats, and it gives you the scores in these squares of how well you did. Okay? So we have all these diagnostic features coming out of this simple little GUI, as well as showing you the network architecture here, which is, again, a replica of this one here. So all of this information is coming to you just as you go train this thing. It will produce all this information of how well it did. So it's important that you look at these things, especially in looking at the errors and the growth of the errors, because you want to see where the cross-validated error happens to start going up. And this is oftentimes when you stop the training, what's called oftentimes early stopping, often has better performance, better generalizability because you don't overtrain. And it's very easy to overtrain on these kind of structures. Okay, let's close these down and look at how we did from the view of performance. So behind here, we'll see our results. So what I want to show here is a couple things. So figure 1, two things that are coming out here in figure 1. So figure 1 at the top is essentially telling you how well you did on the training data set. Okay? So you can see, so what this is supposed to be, this is 1, 0, and this is 0, 1. So what you can see is, actually I got all the dogs right and I missed one cat, okay, on the training. So it does an impressive job in learning on the training data how to classify all the training data perfectly almost. Not quite perfectly, but it only misses one. However, that's not what's important. You built a model called net out of this thing. How well does net do now on this withhold data set, these 40 dogs and cats it didn't see? And that is here in this figure. So what you see now is you actually start making a lot of mistakes. And so, by the way, it doesn't give you back a vector 1, 0, 0, 1. It gives you back some scores in the vector space of the output, y, which can have two values. And this is telling you what those two values are. So you can see that it actually gets the bulk of the dogs correctly, but it actually gets many wrong. And here's what it does for the cats, and I got 5 cats wrong. Okay? So this is more indicative of the error you're going to have in the system. And this looks a lot like the first lecture where we just did AX equal to B. So it does fine, but you can see there's definitely some performance issues. I can also look at this just in terms of the classes command. And the classes command tells you, take those vectors and just turn them into a label, a 1 or a 2. Okay, so this is a little easier to look at. And so when you look at this one here, again, in the first one, all the dogs are labeled 1, and then all the cats are labeled 2. But of course, in the training data set, it gets one of them wrong. But now, here in the withhold data set, you can see you actually got quite a few number of those dogs incorrectly labeled. And here are the 5 cats incorrectly labeled. So this is a little bit better metric, right? Once you turn this thing into the label instead of the 1, 0, because remember, the input to output just gives you back a vector of 2 components. Doesn't try to say 1, 0, or 0, 1, which one you're closest to, but essentially this is what this does. It tells you which label am I closest to. And you can see this is your performance metric. And this is a very simple neural network architecture to train. You saw how easy it is. You can just basically specify everything here, right? You can change how many layers you want. You can change the size of those layers. You can change your optimization routine, and you can also change the nonlinear activation functions that you want to use in building yourself an input to output layer. Okay? So oftentimes those are called hyperparameters. You can make the network bigger, smaller, different nonlinear functions, and these things will oftentimes change the performance metrics, and sometimes you'll find some works better than others. Sometimes there's a big improvement in how they work, and sometimes there's actually only a marginal improvement in how these things work. And so all of this can be done right in here. Very simple structure. One command, train. Everything works from there. So that's going to be it for now. What I do want to talk about in the next set of lectures is how does this actually happening on the back end. So just a reminder that all this is from the book here. You can find the previous lectures and the post lectures after this at databookuw.com, and also there's a PDF of the files here you can have access to, which will give you all the notes you want. But what I want to follow up on is when we're doing this nonlinear optimization, what are the tools we're using? And we're going to talk about 2 major things that need to happen in neural network training. One is this idea of how do you actually optimize this system? So we're going to talk about backpropagation next, and then we'll talk about, further on from that, stochastic gradient descent for doing the optimization, and then go back into some more examples.